All right, so let's talk about scientific notation. It's a nice way to figure out the significant figures, as we just discussed, right? If you have in scientific notation, all the significant figures are right there. You don't have to look any further. There's no calculating. There's no figuring out which side of the America you're coming on. They're just right there. They're put in the style of some number between 1 and 10, so 1 to 9.999 times 10 to the x. If the exponent of the 10 is positive, that means the number is huge. It's a big old number. And if the power of 10 is negative, then we're talking about a number that's between 0 and 1. So often, right, 0.000 something or that kind of thing. And the exponent is going to tell you, so this number here, this x, will tell you how many places to move the decimal. So for example, if we have this huge number, right, here's a huge number, much greater than 1. So when we want to put that in scientific notation, the first step is to move the decimal all the way until there's only one non-zero digit to the left. So we're starting that decimal started here, and it's going to have to jump all these places. And then when it gets here, now there's only one digit, non-zero digit to the left of that decimal. So that's a total of 1, 2, 3, 4, 5, 6, 7 jumps. So the number we're left with is 5.062. And then the exponent of 10 is the power of how many places you move the decimal. So in this case, we moved it 7. That was a huge number to start. So it's 5.062 times 10 to the 7th because we moved the decimal 7 places. All right. If we're going to do this in the other way, so we have a number here between 0 and 1, right? A very small number, a very minuscule bit. Same thing. You're going to move the decimal so there's only one non-zero digit to the left. So now the decimal's here. We have to move it here to the point where there's one non-zero digit to the left. So we're trying to move it there. So to do that, that's going to be 1, 2, 3, 4, 5 jumps. And we get 4.87. And because we did 5 jumps, we're going to raise 10 to the power of 5. But this time it needs to be negative because this number was between 0 and 1. And we were moving the decimal to the right, basically. All right. So it's better to think about this being a fraction of a number between 0 and 1, and this being a huge number, much, much bigger than 1, rather than going left and right, because that tends to confuse people. I've left here some practice. Khan Academy has some nice practice with this, so you can just do these, but at some point you should have learned this. So let's work on, hopefully this is more of a refresher, but I'm happy to work with you if you need a little more help. Okay. Multiplying scientific notation. If you're going to multiply scientific notation, you take these first numbers and you just multiply them. So 2.5 times 3.4 is 8.5. Remember, multiplying, you can change the order. I can't remember the name of that property in math, but basically, if A times B and C times D is the same as A times C times B times D. Anyway. All right, so you multiply those, you get a number. Then when you multiply the powers of 10, hopefully you remember, you just add the exponents. Because they have the same base, you can add the exponents. So 8 plus 3 is 11. So it's 10 to the 11th. Then you just combine everything again. So it's the 8.5 times 10 to the 11th. Okay, now this can be a little harder. What happens if when you multiply those first numbers, 5.7 times 6.8? Oh, look at this. That's not in the nice scientific notation fashion. Okay, so there's one reason why we leveled up. The other reason is now we have a negative, right? We have a negative 2. So negative 2 plus 7 is the same as 7 minus 2. So you have a total of 5 there. So 10 to the 5th. You still combine everything, 38.76 times 10 to the 5th, but there's two things to do here. One, we have to put this move this decimal so that there's only one non-zero to the left. So we got to move it this way, 1. And by doing that, that's making this times 10. So 38.76 is the same as 3876 times 10. Hopefully you see that. Okay, and so 10 to the 1 times 10 to the 5th means it's 10 to the 6th. We convert that to the two significant figures because this had two significant figures and that had two significant figures, so our answer has to have two significant figures. So we rounded 3.876 to 3.9. All right. Like I said, that's leveled up. Dividing is similar, but something of the opposite. So 9.3 and 4.1, you're going to divide those. So 9.3 divided by 4.1, you get that answer. Then you divide, when you divide the powers of 10, you subtract, the opposite of what we were doing before. So 11 divided 10 to the 11th divided by 10 to the 3rd. Now you're going to subtract 3 from 11, and you'll get a total of 8. So, and then you combine everything. 2.2683 can be rounded to 2.3 times 10 to the 8th. And if we're going to level that up, okay, now we have a negative exponent there. And when we divide our first things, we get a weird number. It's not just a nice scientific notation E, one non-zero to the left of the decimal. So when you divide 1.4 by 3.9, you get 0.35897 and a bunch of other things. When you divide the powers of 10, you still subtract. So it's minus 5 minus 8. So minus 5 minus 8 is a total of minus 13. And then when you combine them, hopefully you realize that this is the same as 3.5897 times 10 to the minus 1, right? Because we move that there. That's 10 to the minus 1. And 10 to the minus 1 times 10 to the minus 13, you add those up. Minus 1 and minus 13 is 10 to the minus 14. So I'm not certain that these couple things are necessary, but I taught them because this way you know it. Okay, now let's do some calculating with significant figures. When you calculate with significant figures, you want to make sure that the answer cannot be stronger than the weakest link. Okay, right? The chain can't have a link that's the weakest link is the strength of the chain. The same is true when we're going to do calculations with significant figures. So when we multiply or divide, multiplication. Okay, the answer has to have the same significant figures as the weakest of the numbers that are used. So in this multiplication, we have 12.51 meters and we have 0.00524 meters. When we multiply them, we get 0.0655524. Okay, that's actually meters squared because meters times meters. And then we have to round this number. So this number has how many significant figures? That should hopefully have 4. Actually, I don't even need to do that because this, it'll say 4. This number has 3. So the answer can't have more than the weakest link. And the weakest link in this case is this 0.00524 because that had 3. So we have to round this answer to 3 places, and 3 places is 0.065. And then we're going to turn that into a 6 when we round. All right. So the same is true with division. So here we have 0.006750 liters divided by 32 liters. This has 2 significant figures. This has 4 significant figures. So our answer can't have more than 2. So when you do that in the calculator, you get this huge answer. I should probably make this liters squared. So that's liters. And then we have to round this to 2 places. Drop it there. All right, so hopefully that makes sense. When you're calculating with significant figures, you have the weakest link. One of the 2 will be the weakest link, and that's what you round your answer to, because your answer can't be like this. If you had this as your answer, that implies you measured to all those places, and you didn't. You only measured to 2 places. If you had this as your answer, that implies you measured to all those places, and you didn't. You only stopped at 3. So you have to cut it off. All right, there it goes. All right, so remember, numbers communicate the quality of the measurement. All right, calculating with significant figures, addition and subtraction, the smallest number of significant figures, after aligning the decimal and the original values determines the number of significant figures in the answer. Okay, so if we had 5.44 inches and we had to add to that 2.6103 inches, we line them up so the decimals are lined up. And because this is addition and subtraction, what we want to do is make sure we do it like on a calculator, and then we want to make sure that the answer is not more accurate than the stuff we put in. So you see how this only went to the hundredths, and then this went to the thousands, 10,000ths, I guess. So our answer can only be accurate to the hundredths because that's how accurate that was. So for addition and subtraction, it's a little different. People love the multiplication division one because it's easier to remember. But for some reason, the addition and subtraction, not for some reason, it should make sense. And if we could do a lab, I'd show you this in lab. But anyway, 8.05 is the answer there. So when you're subtracting, same thing, you line up your decimal, you make a line for where the significant figures ended. So the significant figures ended here for the 3380. That's the last significant figure. And so therefore your answer can only be accurate to the tens place. Even though you had these on this number, your other number didn't have it to that point. So you have to round to this place. Okay. And so the way I think about this is if you combine the plus and the minus, right, it forms something that kind of looks like this, right, where you have this lining up stuff. And when you combine a dividing sign and an X, you have this weird thing that looks like something you'd have seen in an ancient cave or something, but certainly not the organization you have here. So the end of the day is multiplication, division, you just use the least number, and addition, subtraction, you got to line them up by the decimal and stop